Gu, and he will tell us about an ambiguous test of positivity at lepton colliders.
Hi, can you hear me?
Yes.
So okay, great, thanks. Okay, thanks. Thanks a lot for the invitation and the introduction. I've been very lucky to be able to attend this workshop in person. It's my first time at USTC, and I've had a great time. So let me start. So this talk is mainly based on this paper here with Lian Wang and Chen Zhang. Okay. I think I just maybe need to click here. Okay, it works. Yeah. So I guess I don't need to tell you what positivity is. We've already had some excellent introductions from the previous speakers, so I focus on the test. But let me just mention that there has been some recent interest in positivity, in particular in the SMET framework. We already heard the talk just now, and also as you probably learned by now, so these bounds only exist for certain dimension 8 or even higher operators. So they don't we don't have these for dimension 6 operators. So basically the statement is the following. I guess you've also seen this already. So I guess it's only the simplest version of it, but it's sufficient for what I'm about to say next. So basically, we just consider elastic forward scattering. Just some particles A and B comes in and then goes basically head to head and comes out. And then the statement is that the coefficient of the S squared term in the amplitude must be larger or equal to 0. And of course, it simply cannot come from dimension 6 operators. There are too many derivatives. So basically, we need 4 derivatives. So it can only come from dimension 8. And so to turn this statement the other way around, so if we can measure these dimension 8 operator coefficients, then we can actually test whether the underlying new physics is consistent with the fundamental principles of QFT, namely analyticity, locality, unitarity, and Lorentz invariance. So of course, we can ask whether we even want to challenge these fundamental principles of QFT, but maybe a more practical question is, I mean, as we all know, it's difficult to measure the dimension 8 operators. So can we even do this test? And if not, does it really matter for phenomenology? Because in general, it's very difficult. So we know those contributions has a large energy enhancement, namely they need to be proportional to e to the 4th. So naively, we would think that LHC should be able to probe them well because LH has a large energy. But the problem with LHC is that because of the parton distribution function, then the events with very high energy also tend to have low statistics, so they are not measured very well. So there's one example from this, so it's actually an actual experimental study from CMS. And as you can clearly see from this distribution here, as the energy increases, then the number of events drops dramatically. And so these events with high energies are not measured very well, but on the other hand, they're also most sensitive to these operators. And so this study actually derived some bounds on the dimension 8 operators. And then these people here actually derived the positivity bounds on these operator coefficients, which is shown by this green region here. And so this looks all fine, good, until you look at the numbers on the axis, then we realize that in this case, and the reach on the scale of new physics lambda is around the scale of the energy of the machine, or even much smaller than that. And in that case, then the EFT expansion just doesn't make sense. So of course, this green region is always good. I mean, I totally trust the results of these people here. But these ellipses here really needs to be taken with a large grain of salt. And this situation is quite general for LHC, even for other processes, I mean, for the reasons I just mentioned. And to make things even worse, we know that usually the dimension 6 operators are the dominant, provides the dominant effects. So can we even separate the dimension 8 from the dimension 6? So it seems that we really need both high energy and also high precision. Then we can measure several different energies and then solve these two problems together. In that case, it seems that we need a very high energy lepton collider. Of course, we may or may not get a collider like that. And so a different strategy is to actually try to look for some process where the dimension 8 could give the leading new physics contribution. So this is the strategy we took. So we actually managed to find a process like this. And so which is, maybe I should. Anyway, so this is actually the process we're all familiar with, diphoton channel. Of course, it's not the SIM50 GeV one, so it's just a standard model non-resonant process at a lepton collider. So E plus E minus to 2 photons, so mu plus mu minus if we have a muon collider. So one remarkable feature of this process is that if we ignore the mass of the electron, then in the standard model at tree level, the only possible helicity configuration is the following. So only this exists in the standard model, which in which case so the sign here denotes helicity. So the 2 electrons and the 2 photons both have opposite helicities. And then for this helicity configuration, then the leading order contribution can only come from the dimension 8 contact interaction. And so basically the amplitude can be written in this form here. So if you are not familiar with the bracket notation, it doesn't really matter. So basically this term here is the standard model one, which has a T channel and U channel poles. And then this is the contact term we can write down just by dimensional analysis. We know it's from dimension 8. And here we just give the coefficient a name. We call it A here. And of course, there are 2 of them. And because there are 2 fermions, essentially, the left-handed and the right-handed electrons. So we have AL and AR here. So if you are an amplitude person, I mean, this is really all you need. So this is your operator, and then this is your Wilson coefficient. But we can also map them to the more conventional sense of operators. And those are also related to those also contributes to the ZZ and Z gamma final states. And so for instance, they were written down in this study here, and also in the complete dimension A basis in these papers here. So for instance, we can write down 5 operators like this, then the connection between these and the AL and AR are straightforward. So for the rest of my talk, I won't really show these operators again. I just focus on AL and AR. Okay, so as we know, normally the dimension 6 contribution would. Is there a way to make this disappear? I guess not. Go back. Okay. So normally the dimension 6 contribution will dominate, but in this case, they're actually either vanish or are suppressed. So let me try to go through this argument. So first, the only tree level dimension 6 contribution comes from a dipole operator, and it generates a different fermion helicity as shown in this diagram here. So since it has a different helicity, then the at tree level standard model and dimension 6 simply do not interfere. But of course, we also need to consider dimension 6 square, which is formally at the same order as dimension 8. So which can come from either this diagram squared or from a double insertion like this. But it turns out that these dipole operators are very well constrained by G-2 and EDM measurements. So if we plug in numbers, I mean, it's just basically too small and it's totally negligible. So of course, we also need to consider the interference between standard model and dimension 6 at 1 loop level. because one loop suppression factor could be comparable with one factor in the EFT expansion. So those could be comparable with the tree level interference between standard model and the dimension 8. But it turns out that these are either very well constrained by other measurements which they contribute at tree level, or forbidden by some selection rules. So one example is this OCW operators, and it can contribute to the diphoton process at one loop level, but it also contributes to the 2W final states at tree level. So basically, if we can measure this, we can also measure this. And this actually has a larger cross section, so and it contributes to this at tree level. So, and once we measure this, and then this operator is constrained well enough, then basically we can ignore its contribution, one loop contribution to the diphoton process. And this argument applies to a large set of operators. So some of them are very well constrained by z-pole measurements. Some are suppressed by the small electron Yukawa or mass. So there's one exception, which is the 4 fermion operators of this form, EETT, so involving 2 tops. So those operators are basically unconstrained if we don't, if the collider does not run at the top threshold. But it turns out that they are forbidden by some angular momentum selection rules pointed out in this paper here. So I think Minglei Xiao gave a talk on this topic yesterday, so I won't repeat his arguments, but it's basically very similar to the Landau-Yang theorem. So for this diagram here, even we can write it down, it just turned out to be 0. And of course, there are also other dimension 8 operators we can write down, but they have different helicities, so they don't interfere with the standard model. So after we go through all these arguments, then we've found that indeed the only leading BSM contribution come from these dimension 8 contact interactions, so just written here. And now we can look at the positivity bounds. Of course, we need a elastic amplitude, but that we just rotate this process by 90 degrees, so it becomes the elastic amplitude of E gamma to E gamma, and then we apply this bound. And after working out everything, then this bound just simply implies that both AL and AR here have to be larger or equal to 0. So now we can look at the phenomenology. So here is the differential cross-section shown here. So where this angle theta is the production polar angle, and then this capital P here is the beam polarization for the electron and the positron. And so here's the positivity bounds we have on the last page, and then we can just plug them in. Then it's quite transparent that these positivity bounds actually applies directly on the cross section. So namely, the cross-section of the diphoton process has to be larger or equal to the standard model prediction, and which holds for any value of any values of theta and also any values of beam polarization. So this is actually quite a remarkable result, because in general we can have all sorts of contributions to the observables, and then only some of them are subject to positivity bounds. So in general, it's very difficult to connect observable with positivity bounds, but in this case we can actually it's almost trivial. So the bounds directly applies on the cross section like this, so which is quite remarkable. And of course, this process has already been measured at lab. So these are the results from the lab summary paper. And quite interestingly, the lab measurements was actually 1.5 sigma below the standard model prediction. So in some sense, you can say that the lab measurements disfavor the fundamental principles of QFT by 1.5 sigma, if you want to say that. But of course, 1.5 sigma is really nothing. So we want to verify, or rule this out. And so we need to look into the future. So this can be, of course, measured much better at the future lepton colliders. So to estimate the reach, we did a very simple analysis just based on the chi-square fit to the beam distributions, and checked it agrees with lab results reasonably well. So first we did it to this kind of Higgs factory type colliders. So either circular collider at 240 GeV or the IC at 250 GeV. So first, there's an interesting statement on the beam polarization. So if we go back a page and look at the differential cross-section, then we see that if without beam polarizations, so these capital P's are zeros, then we can only measure one combination. We can only probe one combinations of these two parameters, namely AL plus AR. So this is reflected in this chi-square plot. We can see that there's a flat direction for the circular colliders which don't have beam polarizations. So if we have beam polarizations in that sense, then we can simultaneously measure the left-handed and the right-handed cross-section. Then we can, it's in that sense, it's quite useful for testing positivity, because we can test the positivity of the left-handed and the right-handed cross-section separately. So this is reflected in this circle here for the ILC, where we can constrain them simultaneously. But on the other hand, and if we assume the positivity bounds hold and impose those bounds, then I guess it's hard to see on this big screen. But so only this, then only this region here, the upper right corner here, is allowed by the positivity bounds. And then we see that we actually don't really have this flag direction here. So even if we impose the positivity bounds, we can constrain these two parameters simultaneously, even without beam polarizations. So that's quite an interesting feature, which we don't get at dimension 6. Of course, we shouldn't forget these are dimension 8 operators. They have large energy enhancements. So high energy always wins. So if we have a high energy lepton collider, it can always do much better. And it can be easily worked out. The scaling can be easily worked out. And we checked a few scenarios which agrees with scaling pretty well. Okay, so of course, as we know, the diphoton process is not complete. So the same operators also contribute to the Z gamma and ZZ processes, but they are actually much more complicated, basically because the Z is massive. Then in that case, we have all sorts of helicity states, and then they all mix with each other. And then in general, it's very complicated. But in the high energy limit, we can still basically treat the Z as a massless particle. And then in that limit, we can basically still apply the argument, the arguments we had previously. So in that case, then for instance, we can write down a similar bound for the ZZ cross section. We can even relate write down a bound that relates the all three cross sections. And then we can also even put the bounds on the three-dimensional space of the cross-section like this. So it looks like a cone, and only the region on the right-hand side is allowed. And but of course, it's this is only true in the high energy limit. So in general, I mean, we can still look at these processes, but they're much more complicated. Okay, how much time do I have? Ah, good, good. Yes, so of course, if we do the measurements, it may turn out that everything is standard model-like, and then there's not much we can say. But what if the results turn out to violate positivity bounds? So of course, it can be a statistical fluctuation or systematic error. As we all know, even phi sigma can go away in the diphoton channel, so we have to be careful. So one possibility is that EFT is not really valid. For instance, we can have a light particle that contributes to this process. But in this case, it can be very well probed either by the resonance searches or just by measuring the diphoton process at several energies, which we can do. And then in that sense, we can really tell whether this deviation comes from dimension 8 operators just by measuring the energy dependence. So it looks like we can easily check this possibility. And of course, we can ask whether QFT can really break down at the TV scale. And I mean, if not, I mean, why do we bother? Of course, there are examples from history that, I mean, nobody expected classical physics to break down. Nobody expected parity to be violated, but the experiment says otherwise. I guess, well, I mean, every Chinese knows the story of these two guys, but it's Lady Wu's experiment that confirmed parity violation and gave these two guys the Nobel Prize. So I guess the message is that it's important to do the experiment, and let the experiment tells us what to believe. With that said, let me conclude. So the measurement of diboson diphoton process at lepton colliders offers a unique opportunity to directly probe dimension 8 operators and their positivity bounds. And remarkably, we can do it at a lepton collider with relatively low central mass energy, around 240 GeV. But of course, high energy is always better. And of course, we built this mainly to be a Higgs factory. So we kind of get these positivities for free. And before I finish, let me just show you a quote from the famous Sherlock Holmes. I guess you've seen maybe seen this quote already. So who knows? I mean, maybe we'll be in a situation like this. I guess it's not too crazy to think about this possibility, and I guess we will see. Okay, thanks.
Maybe we can have time for one quick or two quick questions. Any question in the room, in the conference room? Any questions online? I don't see any question, but I do have a question, naive question. Yeah. So do you expect many of these clean channels to test positive bound in future collider? I mean, you found one. Do you expect that there will be many of these?
Probably not many. I mean, I do have one in the backup slides, which is from your paper. I mean, so that one was a bit special because that one was, I mean, the diphoton one is sensitive to the dimension 8. But in principle, we can look at other processes. This is from your paper. But in those cases, for instance, we can have both dimension 6 and dimension 8. We can have many different contributions. But in those cases, if we can have a high energy lepton collider and preferably also with beam polarizations, then we have can have more handles to separate the effects. And well, I mean, in your paper, you showed that it's actually possible to discriminate these operators if we, for instance, in high energy collider like click, and then in that case we can do much more. And yeah, I mean, maybe if we have a muon collider, that would be even better. But then it depends on the collider.
Okay. Any other questions? A quick one. We are actually running late, so let's break for 15 minutes about.